We ended the last video with performing this calculation, taking the cross product of these two vectors. What we're going to do in this video is discuss lots of cross product theorems, lots of properties, things you're guaranteed to have when you're working with cross products. And I'm going to keep referring to this calculation over and over along with other similar calculations in order to illustrate all of the theorems that we're going to have. So you want to pay careful attention to this one. So V was 135, W is 201. The cross product of V cross W is 39, negative 6. So the first thing that I want to do here is let's interchange the order of V cross W. So let's do W cross V. Again, keeping the same V and W from here. So I hat, J hat, K hat. So now we put W in the W's components in the second line and V's components here in the third line. And so if we calculate out this cross product, we would get, okay, so I hat times cover up the first row and column, 0, 1, 3, 5, minus J hat times the determinant we get by covering up the second row and column, 2, 1, 1, 5, plus K hat times the determinant we get by covering up the first row and final column. Yeah, so first row and first column, first row, second column, first row, third column are the three things that we do here, 2, 0, 1, 3. Okay, and when we evaluate these determinants, we get I hat times 0 times 5 is 0, minus 1 times 3. So that's negative 3 I hat. J hat, so 2 times 5 is 10, minus 1 times 1. 10 minus 1 is 9, times negative J hat is negative 9 J hat. 2 times 3 is 6, minus 0, plus 6K hat. So our answer here is going to be negative 3, negative 9, and 6. And if you're paying attention, does that look somewhat familiar? Don't want to say familiar, I want to say somewhat familiar. Negative 3, negative 9, 6. What answer do we get up here? 3, 9, negative 6. How do those two relate? They are negatives of each other. So this happened to be the negative of V cross W. And that's not an accident. That's not an accident. This is always going to hold true. That W cross V is the negative of V cross W. And so let me get my cross product theorems slide back here. Let's add this to the list. So W cross V is equal to negative V cross W. So the term that sometimes gets used for this is anti-commutative. The cross product is anti-commutative. Normal multiplication is commutative. We can switch the order. 2 times 4 is 8. 4 times 2 is 8. And in the previous section, we saw that the dot product is commutative. U dot V is equal to V dot U. That is not, this is very important, that is not the case for cross products here. W cross V is equal to negative V cross W. Okay, next thing that I want to do for the list here is using the same V. I want to calculate out V cross V. So if we do V cross V, so I hat, J hat, K hat times, sorry, no, I shouldn't say times there, the 135, 135. So V is just the vector components 135. When we evaluate this determinant, we get I hat times cover up the first row and column, And so 3, 5, 3, 5. Minus j hat, cover up the first row and second column. Determinant 1, 5, 1, 5. Maybe you can see what's going to happen here. K hat times the determinant 1, 3, 1, 3. What happens? I hat times 3 times 5 minus 5 times 3. 15 minus 15, 0 I hat. This determinant, 1 times 5 minus 5 times 1. 5 minus 5 is 0. 0 times j hat. 1 times 3 minus 3 times 1. 3 minus 3 is plus 0 k hat. What do we have here? This is the 0 vector. So v cross v in this case is the 0 vector, and that is not, again, an accident here. That is always going to happen. V cross v is always equal to, but let's remember, put the vector sign there, 0 the vector, the 0 vector here. Once again, this is different than the dot product. The dot product of a vector with itself, v dot v, gives you the square of the length of v, which is going to be something positive as long as your vector is not the 0 vector. But here, take any vector, cross it with itself, you're guaranteed to get the 0 vector. In fact, let me do one more riff off of this. Let's say here v is equal to 1, 3, 5, and u is equal to, I'm just going to multiply all of the entries of v by 3. So I'm going to do v cross u, where the entries of u, this is just 3 times v here. So when we do this calculation, v cross u, which is really v cross 3v, I hat, j hat, k hat, 1, 3, 5, 3, 9, 15. We get I hat times 3, 5, 9, 15 minus j hat times 1, 5, 3, 15. That determinant plus k hat times 1, 3, 3, 9, that determinant. And if you crunch out what we get here, this determinant, 3 times 15 is 45, minus 45 is 0. 15 minus 15 is 0. 9 minus 9 is 0. Once again, we get the 0 vector here. And so what's going on here, we cross product v with a scalar multiple of v, or in other words, if we take the cross product of v with a vector parallel to v, we get the 0 vector. So what I can say here is the following: v cross w is equal to 0 if and only if w is equal to lambda times v for some scalar lambda, so v and w are parallel, or v is equal to 0. This is, so take the cross product of two parallel vectors, you are guaranteed to get 0. Okay, one final property I want to discuss here is let's bring the dot product into this. So let's calculate v dot v cross w, where let's go all the way back here to this v and this w here. And so we know that v cross w is 3, 9, negative 6 here. So what we're supposed to do is compute 1, 3, 5, dot product 3, 9, negative 6. So this is going to be 1 times 3 is 3, plus 3 times 9 is 27, plus 5 times negative 6 is negative 30. what do we end up with? We get 0 here. And once more time in this video, I have to say that's not an accident. This will always happen here. That, what does it mean if we get a dot product with 0? What's our word that we should be looking for? Orthogonal. So our final bullet point, look, now I have bullet points here. Our final bullet point here is V cross W is orthogonal to both V and W. Okay, so this is our main set of cross-product theorems. These are the most important ones. Let me just write down, to wrap up this video here, a couple more grouping, associativity, and distributive laws. That if you have a scalar lambda times V, and you do the cross product of that with W, we could also move the scalar lambda to the other side, V cross lambda times W, or we could do the cross product first, V cross W, and pull lambda out in front. And so this is associativity, a little bit of grouping stuff going on here. And U plus V cross product W is equal to U cross W plus V cross W. And I'll just put down etc. So this is, if I have addition on the left, you can also do addition on the right if you wanted to. Okay, so lots of really important cross product theorems. These are really good things for you to know.